Good evening, everyone. The time has gone 7:45. We're going to go live with our discussions and presentation at 8 p.m. But until then, we're certainly going to be talking to each other, having an informal chat and seeing what's happening in all of our lives. So a big welcome to everyone around the world. And we're so happy tonight that we have one of the most preeminent scientists in South Africa, Professor David Block, who's joining us this evening. And he, of course, is a world famous astronomer. And he says modestly he's been on the cover of Nature magazine twice. But let's face it, 99.99% of scientists will never, ever be quoted in Nature magazine. And to be on the cover twice is an absolutely unique, remarkable thing to be able to do. So welcome, everyone. Please tell us where in the world you're joining us from. And Danny Kadar, Britt Landsman, turn on your cameras. Let's have a quick chat.
Hello, Howard.
Hey, Danny, how's it?
I am doing fantastic. Super excited about this webinar. Super excited.
Have you ever thought about having a planet or a star named after you? Because for like $5 or $10, you can actually do that.
Well, now that you've mentioned that, I would definitely take you up on that offer. I did actually wanted to travel to the planets and the stars. I actually did. You know, when you're a child, you dream of being either, cops or a cowboy or a fireman. I wanted to be an astronomer. Maybe it's because I was a nerd, but
not an astronaut. You wanted to be an astronomer, not an astronaut.
I wanted to actually be an astronomer, and I was told if that's the case, I better improve on my maths skills. But I never took up that suggestion at all. So sadly, that fell through the cracks, that dream of mine.
So, Britt, do you ever lie back when you're out in the bush? I know you're a big motorbiker. So when you're on the back of your Harley and you've gone into the middle of nowhere and you lie down in the grass and it's at night, you stare up at the stars and wonder.
Of course, there's nothing better than being out in nature and being able to check out the stars and get away from normal life.
And like, do you ever go and look at the night sky and say, oh, well, that's actually Saturn that I can see, because Saturn's actually quite prominent in the sky at the moment?
I think that's the only one that most people know. Besides that.
Or they think Mars is a little red.
Yeah, exactly.
And
yes, yeah.
And Danny, meteor showers. What do you do? Have you ever been out to see a meteor shower?
I've actually never caught one, which I'm like completely dismayed about it. But yeah, I'm definitely one of those nutters that, to the astonishment of most people, I'm like, guys, did you know that Saturn is going to be the brightest it's ever been in 70 years tomorrow night? And they're like, Daddy, what the hell are you going on about? But that's the kind of stuff that just gets me all excited. What can I say?
So have you ever read, for example, A Brief History of Time, Stephen Hawking's?
I try to understand it.
Which is the book that they say is most purchased and never ever read.
I think I did get through the first 3 chapters before I realized that I am completely out of my depth over here.
Well, when we were preparing for tonight, I said to David Block, in fact, I said, the amazing thing is that there's a chapter on black holes in The Brief History of Time. And I got sucked into the chapter and I couldn't get out. And I feel like Stephen Hawking's proved his point. Nothing escapes a black hole. He should have just put that chapter further back into the book. More people would have gotten further rather than getting stuck in it.
True, 100%. In fact, there's a new Netflix show about I'm sure the professor's going to talk about it, about Hawking's radiation and just the impact that it's had on the astronomical community. Even post his death, now they're starting to unravel how this mad scientist has turned physics on its head, because he literally, post Albert Einstein, was truly like this crazy scientist with these insane ideas, which challenges everything we think we know about reality. So totally.
So if you struggled a little with A Brief History of Time, my favorite Hawkins is actually this one. I don't know if you can see it. The Universe in a Nutshell.
No,
I know
haven't
you keep on lending me books. So Danny, I'm going to lend you this book as well. I'm not sure it's easier to understand, but it's got cooler pictures inside.
Okay, totally, definitely. If you're into that kind of literature, then I really suggest Michael Crichton. Actually, funny enough, although it's fiction, the same author who wrote Jurassic Park, he wrote a book called Timeline, which he's done thorough research on parallel universes, of which just the first half of the book just completely sucks you into the science of parallel universes and black holes. So definitely recommend that.
So I see Aubrey Krawitz has posted, he says, hi from Century City, Cape Town. Looking forward to seeing how our childhood comics have proved to be prophetic. And isn't it actually amazing that so many of the things that I think appeared in our childhood comics actually have reached fruition? And I'm thinking about Mars. And not only do we have rovers wandering around Mars, but we now have a drone that's flying around Mars as well.
And taking the most astonishing photographs. I mean, I could stare at those photographs and just that video footage for hours on Mars. It's like you just cannot believe that you're looking at a completely different world that's literally out of this world. But even going further back, look at Star Trek. I mean, you look at Star Trek in the 1950s, 60s, people were like, what is this nonsense? Like automatic opening doors on a spaceship.
And flip phones. I mean, that was a Starship invention.
Exactly.
A Star Trek invention.
Yeah, so, look how far we come.
Do you think it's just us who had this grand fascination about the night sky and the universe out there, or do you think it's a common theme across people? I'd love to know. And Professor David Block, you dressed up for us. Dave, you're retired. You don't have to wear a jacket anymore.
Well, that's true, but it's just awesome to be here with the lockdown and with the electricity and the load shedding. It's just awesome to finally be here in Krugersdorp, where I have backup generators.
Where you hail from?
In exactly the same little town of Krugersdorp, where there was once clear skies.
And if you looked out of the window tonight, what do the skies look like? In Krugersdorp, are they filled with light pollution or general pollution at the moment?
You know, Howard, as a teenager growing up here, the skies were pristine and so dark. But here, I think you can see the moon and you can see Venus when it's up and a few of the brightest stars. But light pollution has destroyed our skies. That's why you and I have to travel to Hawaii, to Mauna Kea, or to Chile to actually observe the pristineness of the night sky. It's something that is lost, you know, Howard, in most large towns and cities around the world.
So, Dave, we were chatting in the week about Mauna Kea in the big island of Hawaii, where you spent 4 months. I just spent a night. But you actually drive up the mountain and you drive through the cloud level and you come out on top of the cloud level at the visitor center, and you can spend a night with all the astronomers with the telescopes above cloud level. Look at the most remarkable skies you've ever seen. But it's not the southern hemisphere. The southern hemisphere is special, though.
That's right. No, absolutely. When I work at Mauna Kea, you are quite right. The halfway stop is called Hali Pahako. You stop there and you overnight there, and you get acclimatized because, as you know, the oxygen content is so low. And then we climb up, we go by car to the very summit of Mauna Kea, right through the cloud layer. It's an awesome experience. And then the night sky it's like the stars are raining down photons and photons. It's just magical. As you say, it's not the same as the southern hemisphere skies, because here we can see the center of our galaxy, which I'll be discussing tonight, whereas for Mauna Kea, you can't. But yes, to be able to travel through the clouds, right through and right up to the top of Mauna Kea, it really is one of the world's grandest observatories there. And then, of course, I've also worked, as you know, in Chile, in the Atacama Desert, also extremely pristine skies.
The person who gets to work in at the Greenland Observatory, do they have to draw straws for that position?
I suppose they would, yes.
So, David, we also discussed, because I spent some time in the deserts of Chile, in San Pedro de Atacama. And and one of my favorite experiences that you do is they take you out at night into the middle of the desert, where an astronomer has a home, and he gives you wine and a lecture about the stars, and has all the telescopes set up in the middle of the Atacama Desert, and you spend an evening with a Chilean astronomer. Those are the magical experiences that I think most people watching would probably never actually think of doing.
That's right. I mean, very few people have access to these telescopes. Of course, the moment the sun sets, we are on it. We normally start our day, of course, at night, our day observing at about, say, if sunset is, say, 5 p.m. Or 6 p.m., we'd start at about 3 p.m. There are myriads of computers to fire up. You have to rotate the domes. You have to get everything aligned, all the computers buzzing. But then, of course, the magic starts, because you can collect photons 10 billion light years away. It's extraordinary. You know, I use the Spitzer Space Telescope, which is in orbit about the sun. And it's extraordinary. I mean, as this telescope's orbiting about the sun, the photons stream in, and they could be coming onto my computer right here in Krugersdorp. It's absolutely, I mean, it's magical. I think that's why I've often said, Howard, I've never worked a day in my life, because it's just such fun. It's such magic.
I'm actually curious to ask, and maybe we're going to ask this during the webinar, but what do you actually see on that computer screen? Are you actually looking at pictures or images of actual planets or stars, or are you just looking at graphs and data, and have these astronomers just lose their mind because they see something unusual,
It's a lovely question, Danny, and the answer is all the images I'm showing you tonight are secured through, observatories, telescopes, most of them, except for terrestrial ones. So, we actually, for example, if I'm using the Spitzer Space Telescope, you would actually, and you image a galaxy, you'd actually see the galaxy on your screen. Wow. Then you can zoom in, you can analyze a little rectangular section of the galaxy. We might be looking, say, 5 billion light years away. We can take a little rectangle, and then we can actually take slices, cuts, just like they do with teeth, or CT scans. You can actually take cuts through galaxies, and then you can, generate whatever graphs you're interested in. Amazing. Color graphs or temperature graphs or whatever you want. But it is to see photons just float onto your computer screen from, Mauna Kea or Chile, it's another world.
Amazing.
Well, the time has just gone 8 p.m. A huge welcome to everyone around the world who's joined us, and a special welcome to Professor David Block, who is our guest for this evening and whose brains we're going to be picking lots. So, Dave, I see we've got lots of family on for you. David Seifa says, hi, cousin, second or third, David. Thought through your mother, Phyllis. And of course, your cousins to Barry Shube and Wendy Kahn as well. So we probably have lots of your family busy watching you this evening.
Including family, I understand, from Canada. We also have my geography teacher, how about this, who taught me in 1969, Robert Burt, and he's joining us tonight online. So it really is a global experience, Howard.
So, Dave, we're going to take care of housekeeping, which will take us 2 or 3 minutes, and then we're going to have a quick chat to you, and then we're going to get off the screen while you do a presentation, and we're going to come out with lots of Q&A. I must tell you, I have my own set of questions, and I have pages full of questions. Those are just mine. I imagine that the thousands of people who are joining us this evening are going to have so many questions as well, and we really do want this to be a dialogue. So thank you for joining us this evening. We're going to do an introduction of you in a few moments, but a massive welcome to everyone around the world. Our last webinar we did was in fact with the music guru Sean Brokenshaw, and it was so popular and we couldn't allow it onto YouTube because of copyright, so we actually had to broadcast that twice. And we're coming back next week with another whole bunch of amazing webinars as well. But I want to remind everyone that the latest edition edition of the South African Jewish Report newspaper is out. Strongly recommend you go have a look at it. An amazing story on the front page of the newspaper by Paula Slier, telling us about her experiences in Afghanistan with the Taliban, going around. And it's an amazing story. And one of the funniest elements, and I don't want to spoil the punchline right at the end, but one of the amazing story, Paula touches on the only Jew left in Afghanistan. And before, when there were 2 Jews left in Afghanistan, they didn't speak to each other. but this guy insists he's not leaving, he's staying, he's taking care of the shul. But an amazing story about really the Taliban and what's happened. You must go, please collect your edition of the South African Jewish Report. You can get it, I'm sure you know by now, at Pick and Pay and Checkers and Exclusive Books and CNA and your local garage shop. They're all over the place in about 240 locations. So please go pick up your hard copy of the Jewish Report newspaper. And if you're unable and you're not leaving your home or unable to get a copy, please go to www.sajr.co.za. You can download the entire edition from our website, or alternatively, look at each of the individual articles by themselves. But it's a great edition out, and I strongly recommend you go do it. And also, please don't forget that nominations are open for Jewish Achiever Awards. So please go and nominate. We've got 9 categories ranging from women in leadership to business leadership to entrepreneur, community service, humanitarian, lifetime achievement, business leadership, professional excellence. Go and nominate your candidates. Nominations are absolutely flooding in at the moment. We've got about 2 weeks left before nominations close, and we certainly want you to have your say. Nominate your people. You'll also get an opportunity to be able to vote in the not too distant future as well for your favorite candidate. But our judging panels are being put up at the moment, so definitely very keen for you to participate in that process as well. Also, please don't forget, very importantly, Limud this coming up this Sunday. So that's why we're not broadcasting on Sunday. We're giving Limud an opportunity to in fact have their guest speakers on, and we'll be back again on Thursday. At the bottom of your screen, if you're watching us on Zoom, don't forget there are 2 buttons. One is a chat button. Please feel to chat amongst yourselves, post comments, whatever you want in the chat section. This really is the town square of our community and from people around the world. So please use the chat section. But if you have any questions for David, please go and click on the Q&A button at the bottom of Zoom, and we'll make sure that David answers your questions. He's going nowhere tonight, even though curfew kicks in at 10 o'clock, and he's had to run to Krugersdorp to his son because there's an inverter there, and Eskom doesn't know if they're keeping our power on or off this evening. David says he'll take as long as you want to answer all of your questions. So please make sure you use that Q&A button at the bottom of your screen if you're on Zoom. And if you're watching on YouTube or Facebook, because we're broadcasting obviously there as well, and so many people actually prefer YouTube because they throw it up onto their screen, entire families watch together. If you're watching on Zoom or on Facebook, don't forget, just leave a question or a comment in the comment section on either of those 2 platforms, and Danny and Britt will bring that information through and ask the questions on Zoom tonight. So Danny and Britt, if I can ask you just to turn on your cameras and wave at everyone. Thanks, guys. Thanks for being on control tonight. In fact, we're booting Britt off. We told her she can go lie in bed and watch us. So Danny's actually told us that there's no way he's missing a moment of tonight. He's staying on. Britt, go and enjoy. But David Block, I have one question for you. If you were to design the perfect dinner party, who would you have as your guests?
Well, if you asked me that a couple of years ago, definitely Stephen Hawking and Nelson Mandela. I suppose at the current epoch, amazing people like Auschwitz survivor Dr. Edith Eger. She's absolutely amazing. She's in her deep 90s. But as far as astronomers are concerned, possibly Kenneth Freeman, one of the fathers of dark matter. Interesting, my selection, Howard, would always be astronomers, really, or great minds. Also someone like Lord Martin Rees, who was the astronomer royal. Not too many politicians on my list, but possibly, yes. I think I'd also like to have Barry Schubert at my home because he hasn't been there yet, although we are cousins and we talk on WhatsApp. But mine's like his are legendary. And I'm also very keen to meet Adrian from Discovery. I think a dinner there. It's people like that who are really thinkers of tomorrow and, you know, pioneering thinkers out of the box. Those are the kinds of people I'd love to have around my dinner table.
And
if that's happening tonight.
If you had a choice of one guest, and I gave you the choice between Isaac Newton, Albert Einstein, and Stephen Hawking, who would you choose?
I'd choose Galileo.
He's not on the list.
Okay.
But I appreciate my list is limited.
Exactly. I think that I would love to talk to Einstein about the interface between art and science. Einstein loved music, and I think it's a beautiful avenue to explore the interface between art, the world of art, and the world of science. So certainly he'd be right on top.
So I see one of the questions that came up is, are you in the queue to go to Mars? And your son answered it and said, you're frightened of heights.
Yes, you know, the thing is, I'm not here for billionaire rides. At the moment, SpaceX and all these other rides, Howard, are billionaire rides, you know, Bezos going into space and so on and so on and so on. I'm in for the long haul. I mean, I was asked on the 702, would I like to go into space? Yes, if I had the opportunity, I would, but not just for 5 minutes. You know, I'd like to spend some time up there. Like, for example, I think that if one linked up or docked with the International Space Station and one did some real science, that makes the time all the more worthwhile. But to me, I've got no real desire to go to Mars because there's no atmosphere there to talk of. But I suppose I'm terrestrial bound. But as I was saying to Bruce Whitfield the other night, if someone gave, I think it was 400 million rand or something like that. Jeff Bezos' flights up there. It's something to consider, but at this stage, it's not really serious science.
So David, very, very quickly, Barry Shube says, gosh, David, bowled over. Many thanks for the compliments. Looking forward to a great presentation. And we have Paul Plumberg asking whether Patrick Moore was ever an influence on your life. I'm sure we'll.
That's a lovely question.
I'm sure we'll cover all of those questions in a moment. Just give us a brief inkling. What are we going to be watching over the next while? And tell us about tonight.
All right. So I've divided the lecture tonight or the presentation, the talk, into the fireside chat into 3 sections: black holes, dark energy, and dark matter. And then also, because you got stuck on that chapter on time, I'm asking the question tonight, what is time? And I'll be unpacking the thoughts of Stephen Hawking. So it's black holes, dark energy, and dark matter. And then finally, what is this enigmatic concept known as time?
So Dave, just before we begin, we compiled, which we in fact sent out, a little introduction of who you are. We're just going to play it quickly, and then I'm going to turn off my screen. I'm going to leave that to you, and I'll come back during question and answer time.
Awesome.
But for people who don't know you, who never came to watch you at the Linda Auditorium or see any of your other talks, here's a little background to understand who is Professor David Block.
2, 1, 0, all engine running. Liftoff, we have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. That's one small step for man, one giant leap for mankind.
Space Shuttle Atlantis to assemble the framework for the science laboratories of tomorrow.
Houston now controlling.
and slipped the surly bonds of earth to touch the face of God.
The world-famous astronomer David Bloch is a boy chick hailing from Krugersdorp, an erstwhile prominent Jewish town
where there were plenty of forays.
In those days. Krugersdorp still had clear and dark skies, perfect for a serious nerd to start his exploration of the heavens.
A source of constant solace to astronomers is light pollution.
Such was his fascination with astronomy that it led to hours and hours of study and observations. Not surprisingly, he was elected a Fellow of the Royal Astronomical Society of London at the age of 19. His first research paper on relativistic astrophysics was published by the same society the following year.
This brought his mishpocha loads of numbers.
David has been a visiting research scientist at Harvard University and the Australian National University, and has twice spent months at the Institute of Astronomy in Hawaii,
where studying heavenly bodies is the norm.
Not long ago, galaxy legend Professor Frank Xu invited David to fly to China to speak at a conference at Qingdao University.
David had the chutzpah to request a premier economy seat from Johannesburg to Beijing.
David has published many academic research articles and has written a few books. He is a bit too proud of the fact that he and his collaborators' research has twice been featured on the cover of Nature.
And by the way, Nature is not a magazine on gardening. Besides, David hates getting his hentelach dirty.
This honor created quite a few foibles amongst certain colleagues. Because an academic in South Africa is deemed not fit for purpose after the age of 65, David Bloch now serves as Emeritus Professor at the School of Computer Science and Applied Mathematics at Wits University. The emeritus status gives him the right to have an office on campus to store the books that he can't fit into his home. David learned some Yiddish from his Baba.
He finds expressions such as "Ir hot spelkes in tochas," he's got pins in his bottom, and "Ir hot a matzah ponem," he has a matzah face, particularly appealing.
He enjoys a nosh on a bissel bagel and salmon, and adores traditional borscht soup. David is married to Elizabeth, a lecturer in geography and environmental management at the University of Johannesburg. Together, they have 3 sons, Aaron, who's 29, and twin boys, Nathaniel, Ketile, the chosen one, and Tevya Nkwezi Star, age 23.
Their Xhosa names were given by Nelson Mandela after a visit with him shortly before their birth.
Professor David Bloch, the floor is now yours. Dave, the floor is yours.
Thank you. Do we have a good link, good screen? Yes, you can see everything, Howard?
We do indeed.
Okay, great. We go. We have liftoff. A hearty welcome to everyone around the world who's watching this presentation, unlocking the secrets of the universe, especially prepared for Howard and his all team members of the SA Jewish Report. What Howard didn't tell you is that our common adoration is gefilte fish. Gefilte fish, was ken sein besser? Ich bin taka a große Fresser. Yiddish to English, gefilte fish, what could be better? I'm a great eater of gefilte fish. I'd like to dedicate the talk this evening, the little fireside chat, to my daddy, Leon Bloch, who built my first observatory in Krugersdorp, where you are hearing me tonight. And you see Leon standing in the middle, flanked by Ken Freeman and myself. Our technical guru tonight in Krugersdorp, who's taken over at very short notice due to the load shedding, is our son, Nathaniel Bloch. We gaze upward at the night sky, the Milky Way. The photons rain in from the Via Lactea, the way of the milk. It's an awesome moment just to reflect, to stand under the quiver trees and to look up in awe with a sense of magic and in wonder. Exactly what are these twinkling jewels in the night sky? Well, each star is essentially a sun, a blazing ball of hydrogen gas. And hydrogen fuses into helium at the core of our sun. The temperature is around 16 million degrees centigrade. And you can see these gaseous leaps from the surface of the sun called solar prominences. And one Earth, it will take 40 Earths, in fact, to fill up the spatial extent of simply one flame or one solar prominence on the sun. But the sun is by no means our largest star in the sky. Here we have a schematic of the sun compared to a very well-known star, Arcturus. And you can see that there are stars far bigger than the sun in our Milky Way. In fact, this one almost blows the mind. I was looking at Betelgeuse yesterday morning, in fact, in the constellation of Orion. And here you have Betelgeuse and Antares. And the sun now is a pixel, which means the sun is just a little pinhead in size compared to these stars suffering from stellar obesity. A huge range in the mass, in the temperature, and in the sizes, and in the lifetimes of stars. So these are essentially the constituents of our galaxy, the Milky Way. Now, in our sun, I mentioned that hydrogen fuses into helium, and that gives rise to an outward radiative force. Astronomers call this a radiation pressure. So you've got this outward force generated second by second by second in our sun. But then, of course, you've got an opposing force of gravity. Gravity wants to make the star smaller, to pull the ball of gas inward, whereas the radiation pressure keeps it outward. So a stable star is in equilibrium, maintained by two forces, gravity and radiation pressure. But what happens when the sun uses up most of its supply of hydrogen gas is that there's no longer any dominant radiation pressure, and gravity takes over. And as gravity takes over, a star collapses further and further inward as it approaches the end of its thermonuclear life. The focus is no longer on any outward radiative forces, and the result for a massive star collapsing is a stellar black hole. And we'll be digging into this. I've devoted much of my life to studying black holes, their geometry, their curious space-time geometry around black holes. And we'll be delving into this, and I'll be happy to answer any questions. So as a star collapses, once it's exhausted its thermonuclear fuel, or most of its thermonuclear fuel, electrons start floating around. They become dissociated from their parent nuclei. And so you have a sea of these degenerate electrons, which are negatively charged, and that can actually halt the collapse. And that happens in the night sky. We've observed this often. The result is a white dwarf. For example, the brightest star in the night sky, Sirius, has a companion, Sirius B, which is a white dwarf. Here's another beautiful example. Danny was asking me, what do we see through telescopes? This is what we see through telescopes, the Helix Nebula, known as NGC 7293. And this is what will happen to our own sun. Our own solar system will start looking like this in 5 billion years yonder. And the central little dot at the center of the Helix Nebula is indeed a white dwarf, very energetic white dwarf. Now, let's suppose you've got a massive star collapsing and the pressure from degenerate electrons is not sufficient to stop the collapse. Then neutron stars are formed when the sea of negatively charged electrons combine with the positively charged protons to give you neutrons. These are amazing stars. You can see the chaotic magnetic field lines everywhere as charged particles whip around these spinning neutron stars seen here in a computer simulation. But Howard, what I've prepared for you here is a photograph, an image, digital image photograph of the Crab Nebula, an exploding star in Taurus. And at the heart of the Crab Nebula, right in the center, is a rotating neutron star. So to recap, when stars collapse, some can form white dwarfs, others can form neutron stars. And here we have a neutron star at the very heart of the Crab Nebula in Taurus. There are two limits I'd like to introduce you to, the Chandrasekhar limit and the Tolman-Oppenheimer-Volkoff limit. If a star is more massive than 1.4 times the mass of the sun, then it cannot form a white dwarf. That's why our sun will collapse to form a white dwarf, because it has a mass less than the Chandrasekhar limit. If it's more massive, can collapse to form a neutron star. That limit is called the Tolman-Oppenheimer-Volkoff limit. Now, stars more massive than this, like 20 solar masses or 40 times the mass of the sun, simply collapse inward and inward and inward and inward until nothing can stop the collapse. Gravity takes over completely, and we have a black hole. While other people, other guys, were eyeing out heavenly bodies at Clifton Beach, this is what I did at 19. This is the year 1973. And I'm thrilled to see in Q&A so many people coming live on the audience, people I've actually lectured to over the years. I guess that my classes were normally 500 students each year, and I've been at WITS, probably for 40 years almost. So in 1973, when I was 19, I wrote this paper, General Relativity and its Applications to Selected Astrophysical and Cosmological Topics, and I developed a very intense interest in black holes. Now, what is a black hole? A black hole is a region of space-time where gravity is so intense that nothing can escape. The escape velocity is equal to or exceeds the speed of light. Black holes, however, can be of any size. The math gets slightly rough. This is called the Schwarzschild metric, following the metric tensors of Minkowski space-time. ds squared is g alpha beta dx alpha dx beta. And I don't want to go into all the math, but the point is that what I'm trying to say in this image is, in the slide, is that we've got all the mathematical tools. This is amazing. We've got all the mathematical tools to study these enigmatic black holes. Now, if our sun were to collapse to form a black hole, the radius would be very, very small. The radius would be around 3 kilometers. And that's called the Schwarzschild radius, after the great mathematician Carl Schwarzschild. And the density of matter, interestingly enough, as it crosses the event horizon, which is really the boundary of no escape, scales as the inverse of the square of the mass. What's very interesting, of course, and this is, you asked me who I'd like to have at dinner, is Einstein. Einstein's theory of general relativity is that space-time is not flat. Space is not flat, space-time is not flat, but in the presence of gravity, space-time is warped. Just like a rubber sheet analogy, place a little brick or sphere of iron on a rubber membrane, and it causes the rubber membrane to sag. This is one of the great breakthroughs of the great Jewish boy, Albert Einstein. Now, Stephen Hawking and others developed some incredibly strong mathematical theorems. The one was that black holes have no hair. So what it means is that a black hole is uniquely characterized by only 3 parameters: its mass and its charge and how fast it's spinning. In astrophysical terms, its angular momentum. What Stephen Hawking did was totally ingenious. He was able to identify in his mind the possibility of black holes forming, which are microscopic in size. And these are called primordial black holes, which would form at the early stages of the Big Bang universe. Here you see Stephen Hawking together with Nelson Mandela, and I'm sitting just behind the camera. And on the right, you can see the formation of these primordial black holes, very, very dense, very small, but very, very dense regions in the early epochs of our Big Bang universe. Now, primordial black holes have never been observed. They're a hypothetical type of black hole, but the point is, I'm totally convinced that they actually do exist. They have small masses, you know, typically the mass of a mountain, around 10 to the 15 grams. And what Stephen Hawking, is that these primordial black holes can actually explode. It goes against all the classical notions of black holes, that nothing can escape from a black hole. If black holes are microscopic or primordial, black holes, in fact, can explode with a power shoot of around 1 million megatons of hydrogen bombs. This is all extremely interesting stuff. And Stephen actually published his work. I was 20 in 1974, and I remember these papers very well. This one was in Nature, Black Hole Explosions. And what really happens here is that quantum gravity is considered in conjunction with general relativity. But I suppose when you look up at the night sky, here we are at Sossusvlei, and we're gazing up at the night sky. I take groups of people around the world, often to Finland or Norway, to see the aurora borealis. As we look at our galaxy, and here we see shooting stars or meteors, we look at the center of our galaxy, which is in the constellation of Sagittarius, which Howard and I were just mentioning a little earlier. That region is not visible from Mauna Kea. But the interesting thing is that at the galactic center, at the center of our Milky Way galaxy, lurks a very interesting supermassive black hole pronounced Sagittarius A star. It's a very bright source right at the center of our galaxy, located near Sagittarius and Scorpius. But what's very interesting is that this mass of this black hole at the center of our galaxy is around 4 million times the mass of the sun. It's 22 million kilometers in radius. To give you an idea, the average Sun-Mercury distance is around 60 million kilometers. So this is around a third of that. And this is all very current. Reinhard Genzel came to my birthday party in the Seychelles recently, and Reinhard Genzel and Andrea Getz were awarded the 2020 Nobel Prize in Physics for this discovery, while Roger Penrose also was awarded the Nobel Prize. He was able to prove that objects collapsing in towards black holes, the matter goes towards R equals 0, and that singularities are absolutely unavoidable. But how do you actually image black holes if no photons can ever emerge from a black hole? How do you image them? Well, it's very, very interesting, because we can observe them indirectly by means of their intense gravitational force fields on neighboring clouds of gas. Just like this little imaginary astronaut is looking down upon a black hole, but you can see it's there because gas starts swirling around it. Now, how do we actually photograph a black hole? We use a telescope whose diameter is the size of the Earth. Now, that might sound rather strange to have a telescope as big as the Earth, but we do have them. They form part of what's called VLBI, very long baseline interferometry. And essentially, you've just got a whole lot of telescopes, different dishes around the world, all pointing up at the same source. In this case, the center of the galaxy, or wherever you want it to point. So we have arrays, telescopes in Hawaii, in Alma, in Chile, in the South Pole, in Spain, in Germany, and so on. And they essentially all point to the same area of the sky, and we are able to therefore capture photographs of black holes millions of light years ago, because we've got this immense light gathering power, as it were. And the analogy is this. I often explain it to my students this way. In a rainstorm, the greater number of barrels, the greater is the degree of the number of raindrops collected. You know, if you've got 3, you get a certain number of raindrops, but if you've got 10, you collect many more raindrops. And so if we start thinking of telescopes, the greater the number of telescopes all pointing heavenward to the same source, the greater is the number of photons collected. And you can secure the most incredible images with this VLBI technique. Here was a photograph which riveted the world. It was released in April 2019, as far as I recall. It's the first ever photograph of black hole. And I'm so pleased to be living in an epoch when we actually can photograph. I mean, this is stunning. You're actually seeing the gas cloud swirling in around towards the inner dark black hole. Because we're using a telescope the size of the Earth, we can image this black hole, which is 55 million light years away in a galaxy known as Messier 87. And it has a mass of around 6.5 million times the mass of the sun. So to recap, we cannot photograph a black hole directly, but we can photograph clouds of gas being sucked from neighboring stars onto the black hole. Astronomers refer to this disk as an accretion disk. And this is the way we photograph black holes using telescopes the size of the Earth. Galaxies in general are the building blocks of our universe. Now, this galaxy looks very quiet, very quiescent, very tranquil. But I looked at this galaxy and said, no, I think it's been up to some very naughty tricks. I think there's been a head-on smash. I just had this instinct that there's been a head-on smash in this galaxy, that one of these little rugby ball-shaped objects actually has plowed right through the galaxy. You don't only get high energy dynamics in black holes, but also around galaxies. So we used the Spitzer Space Telescope to slice it up into little tile sections, rectangles, to see if my intuition was right. And it was right. This was a paper. I was the principal investigator of a huge team. This was published in Nature a little while ago, I think 2006. And we proved that there was a head-on collision in this galaxy. So galaxies are extremely dynamic. That's why I love astronomy, is everything's moving and colliding and orbiting, and it's just such fun. Here's a wonderful little press release. I was so chuffed. At the bottom left, you see NASA, JPL, Caltech, and our team. And this actually proves the point that galaxies collide, and you've got rings of fire, veritable rings of fire, as these head-on collisions take place. So the building blocks of our universe are galaxies. A galaxy contains, on average, 1 million stars, which is 1 followed by 12 zero stars. Now, here is the rub. Using the large telescopes, which I'm privy to use, we can actually start mapping the distribution of galaxies in the sky. Every dot here is not a star, but a galaxy. Every dot that you see here is a galaxy. Every dot here contains around 1 million stars. Every dot that you see in this image over here, every little dot that you see here spans, in some cases, millions and billions of light years. You can see 35 million light years. This forms what astronomers call this the cosmic web, where billions of galaxies are simply scattered in our universe. Here's another view of the cosmic web. We studied this somewhat in Hawaii. There are great walls, just like the Great Wall of China. You've got great astronomical walls spanning millions of light years. And again, every dot is like a Milky Way. Please understand that every dot's not a star, but every dot is a galaxy. And so we have the formation of galaxies from the universe having an age of 500 million years to around its current age of around 10 to the 17 seconds or 13.7 billion years. And the structure is astonishing. We are living at a time where these largest of telescopes can actually map out the minutest of filamentary structures of galaxies in an expanding Big Bang universe. But there are two unknown forces or two unknown constituents of the universe: dark matter and dark energy. Now, what are these? Dark matter is simply matter which emits no radiation at all, no light, but whose existence we infer from its gravitational influence. It's as simple as that. Whereas dark energy is an unknown form of energy which causes our universe to accelerate. Now, I'll delve into them very quickly. this is quite interesting, is that all the matter I've ever observed in the universe comprises around 4.5% of the universe. Dark energy constitutes about 25%, a quarter, and dark energy around 71%. So about, it's interesting that only around 4.5% of the universe is actually visible. That's quite curious. Now, here's a galaxy, the Sombrero Galaxy, and you immediately think to yourself, well, this is it. There's nothing more than this galaxy. But watch this. See, there's vast halos of stuff around the Sombrero Galaxy. This is just part of the halo extent of what we astronomers start referring to as dark matter, which is much larger than even the halo seen here. Or another galaxy, Messier 83, NGC 5236. Watch that. There's a huge halo. Let's see where the optical image fits. There it is. So you see there's vast amounts of unseen, undetected matter in galaxies. It's an extremely interesting field, the field of dark matter. Now, how do we detect dark matter in galaxies? Well, it's very easy. We plot the velocity with which stars orbit the center of galaxies as a function of their distance from the center of the galaxy. And what we find is something, graphs like this, which flatten out. Notice they don't fall, but they flatten out. Now, what does this flatten out really mean? Well, this is the mathematics behind it. I don't want to worry about that too much. But what should happen if there was no dark matter is the graph should look like this. And if you look at our solar system, where the sun constitutes about 99.9% of mass in our solar system, the planets constitute almost nothing. And so when you look at the rotation curve for the planets in our solar system, it indeed falls in a Keplerian fall-off as 1 over root r, where r is the distance. So Mercury, Venus, the Earth, Mars, Pluto goes around the sun far slower than does Mercury. But when you go to galaxies, there's a huge surprise. You look at the rotating galaxies, some stars are blue shifted, other stars are red shifted. And here is a lady we must acknowledge as one of the greatest Jewish astronomers of recent times. She has since passed away. She was my thesis examiner for my doctorate, Vera Rubin. She worked at the Carnegie Institute of Washington. She is regarded as one of the greatest pioneers in this specific area of the detection of dark matter. And so what you find is, and what Vera Rubin found is that when you look at galaxies, the rotation curve does not fall off, but it flattens out, which means there's huge halos of unseen dark matter out there, comprising around 25% of the mass in the universe. So to paint this in a nutshell, you've got our Milky Way galaxy, for example, right in the middle of the schematic, and the sun and so forth. But then you've got this huge halo. You really don't know how far it extends of dark matter. What's interesting is it doesn't matter which telescopes I use. I can be at Mauna Kea, I can be using telescopes in Chile, I can be anywhere. I can be using the Spitzer Space Telescope. There's this halo. We don't see it, but we see its effects, its gravitational effects, because it's causing the stars near the outskirts of the galaxy to be rotating as fast as those towards the inner parts. So something's causing those stars to move around at these incredible speeds, and that is dark matter, but we don't know what it is, except we can compute its mass at around 1 trillion solar masses. If anyone's really interested to follow this up, Professor Ken Freeman, who's one of the pioneers of dark matter in the cosmos, and I teamed up. I was invited to be a research scientist at ANU, the Australian National University, and we spent a couple of years writing this book together called Shrouds of the Night, Masks of the Milky Way, and the awesome new view of the galaxies. And then Also, I thought I'd prepare a few schematics on this incredibly interesting concept of not only dark matter, but dark energy. Now, this has the opposite effect of gravity. Gravity tends to take, say, two galaxies and to attract one to another, according to F equals gm1 and 2 over r squared. Whereas here, you've got an opposing force. Einstein introduced this, actually, the cosmological constant lambda. It's a repulsion of matter. We don't know what it is, but again, we can infer that it's there. So on the left of the schematic, we put here, this is exhausting, is the gravitational tug, but something is causing the universe to expand outward and outward, to accelerate faster and faster and faster. And our expectation is wrong in that gravity should win. In other words, the universe should start collapsing, but it doesn't. It's accelerating outward. Galaxies are accelerating outwards second by second. And what is causing this is dark energy. So the expectation that the universe is recollapsing is totally false now. We can rule that out. Dark energy constitutes around 75% of the mass in the cosmos, but none of us are able to work out what it actually is, although we can infer its existence. The way we can infer its existence is to look at galaxies in the top frames, and then supernovae start popping out. These are exploding stars. I showed you an example of Messier 1 in the Crab Nebula in Taurus. And here these supernovae pop out. We call them in technical terms SN1A type supernovae. And they are so bright, they explode, they're so bright, we can see them over billions of light years, and they help us prove that the universe is accelerating. But what is actually causing this acceleration, no astronomer knows at the current time. If we plot the data, you can see that we no longer fit on a recollapsing curve. So the notion that we start off with a big bang and the universe then expands to a finite size and then starts collapsing inward is ruled out. The universe is not only flat, but it's following the lines of the on the yellow line. It's accelerating outwards. So if you plot the average distance between galaxies according to time, past and future, and the look-back times of the supernova are extremely large, sometimes billions of light years, billions of years, we come to this astonishing conclusion that the universe is in fact accelerating. And what's causing this acceleration is dark energy. So you've got dark energy and you have dark matter. I think that this should shock everyone who's watching me tonight, live here from Krugersdorp, and that is how little we actually know. In that the matter we understand, all the planets, the comets, the stars, the galaxies, the black holes and more, constitute only 4.4% of the total mass energy content of the universe. 71% is in this very enigmatic dark energy. No astronomer yet knows what is dark energy, what is it actually made up of? What are its constituent parts, in quotes? Dark matter, 25% of the universe. The matter is dark, doesn't emit any radiation. Again, we know that dark matter is there by means of its gravitational influence. We know that dark energy is there because galaxies are being pushed out and accelerating by means of this unknown force. But the matter we observe with telescopes. If I were to stand outside the skies here in Krugersdorp, that would constitute only 4%. And so there are many Nobel Prizes to be won here, where if we could finally crack the code of what is dark energy and the enigmatic dark matter. And so my understanding of the universe is as follows, is that the universe starts off in a big bang around 13.7 billion years ago. Quantum fluctuations are very important at early epochs, which simply means that we must use quantum gravity at these early stages and not only classical general relativity. The universe then inflates outwards at huge rates. We can plot this, we can observe this. It's called the cosmic microwave background radiation. It creates an afterglow of the Big Bang. It's very interesting to study, which is about 375,000 years post-Big Bang. Then you have an epoch of what's called the Dark Ages. Then the universe starts cooling down, and galaxies start forming, and planets start forming, and thus forth. And eventually, the galaxies start accelerating outwards, and you've got this accelerated expansion caused by dark energy. And I think the schematic really sums up the incredible insight, not only of Albert Einstein, but the incredible insight of myriads of teams of astronomers. I've been privileged to work with some of them, of course, such as Professor Giovanni Fazio at Harvard. And it's astonishing that we can actually map the early universe, the afterglow. We can map the acceleration of galaxies. We can actually look back to almost or close to 13.7 thousand million years when our universe first came into existence. And the final topic I want to consider, we've considered black holes and then dark energy and dark matter. The final one is very interesting, and this is really Stephen Hawking's playground. And as was mentioned during the chat, he wrote this book, The Brief History of Time, and it's one of the most popular books ever sold, but it's the book least ever understood. And so I want to try, once Howard invited me so graciously to speak here tonight, I want to try and unpack this so that you'll understand a brief history of time in a very short time frame. And that's going to be my challenge tonight. Right, now, all of us know about the existence of time. Well, how do we know about the existence of time? Well, the most obvious one is that we can measure time. We can measure it. We can take perhaps one of these antique clocks and measure the passing or the passage of time. But as I've explained to my students over many years, this doesn't tell us what time is. It's telling us properties of time, that time flows. But it doesn't tell us what time really is. So Stephen Hawking looked at this very closely, and he was determined to unpack the secret of what the answer to the question, what is time? And of course, today we have digital watches. We no longer wear, you know, the watches with the clock faces and so on, digital and so forth. But there's this passage of something, 11:02 p.m. But what is it telling us? What is 11:02 p.m.? And this is what I have tried to unpack for you, and also in my career. So let's just have a look very briefly at lessons from time. We all know that time has a beginning, just like we have. And as Howard so graciously said in his introduction, I'm the proud daddy of twin boys. And of course, they emerged in our cosmos of space-time with a definite beginning. Let's have a peek. So at top is Tevye, Lewis, and Nkwezi block. The Xhosa and Nkwezi means star, given to him by Nelson Mandela. He had a beginning in time. The birth marked the emergence of the unique mindset, the neurophysiological processes of little Tevye block. And here we see Nathaniel, who's my technical guru tonight, much younger there at school. So he's actually holding a piece of moon rock collected by the Apollo astronauts worth untold billions of dollars, but it was flown out and I was allowed to handle it. And some Nathaniel's V. Katile block, Xhosa, Katile, the chosen one. His schooling had a beginning in time. So we know that one of the key properties of time is that time does have a beginning. We also know that time is direction. Time is always ticking towards the future, never towards the past. For example, you think of Elon Musk with the launch of SpaceX, the docking with the International Space Station. There's a flow of time. Time flows from the past to the present to the future, but it still does not tell us what time is. So there's a paradox here. Time cannot be defined. And some of you very graciously said that I lectured to you and that the exams I set were extra special. Yes, that's true. They were always known as the block specials. The pass rate in this section of the course was always 10%. It never changed. 90% would repeat. The paradox of time. They were always greatly intrigued by this. Very difficult concept, by the way, mathematically. But time cannot be defined. We know properties of time, that time is the beginning and that time flows from the past to the present to the future, but what is it? We can't define it. And I've argued in our book with Ken Freeman that time is masked. Now, a mask is a screen, a shield, a cloak, a shroud. Time is camouflaged. I fervently believe that. Time is camouflaged. It's disguised. There's something there which we do not, or which most people do not appreciate. It's shrouded. You look at your watch, but there's something happening inside of the watch which is telling us something. And I was determined to find out what this was. I'd like to give you a medical example, if I may. If you look at, for example, a spine, you can't optically see a spinal column. So our skin is a mask. The spinal column's there, but you need special eyes, X-ray eyes to see it. It's there. So the spinal column is there, but it's masked. We did not say it's not there, but we need new eyes. And so I was determined to undertake journeys to certain parts of the world to unpack what time really is. So when did time begin? Well, I've already shown you that if you plot the radial velocity of galaxies versus their distances, you know, the universe, the galaxies are accelerating outwards. But if you play the movie backwards, you can see at the near towards the origin, there's a beginning to time. That's interesting. Time has not always existed. Another property. Time has not always existed, but time has had a definite beginning at the Big Bang. Before the Big Bang doesn't make sense. You know, I was on 702 for what, 20 years or more? And people often ask me, Prof, what's outside of the Big Bang? What was God doing before he created the Big Bang? Those questions do not make sense, the word before, because there is no time, because time comes into existence at the time at which the universe is created. So time has a beginning. But let's remember that beginning is a fuzzy concept, very fuzzy. Let me give you an example. When did my life begin? When did your life begin? At conception, at birth, at the birth of your mama, at the birth of your baba, your great-grandmothers. When did time begin? See, when did your life begin? It's fuzzy, not discrete, it's fuzzy. And I was determined about 20 years ago to try and unpack the fuzz. And I'm going to show you the results tonight. So Stephen Hawking made some very interesting claims that the universe can be of a finite age without a beginning. I'll try and unpack that, and that the universe can be finite in time without being bounded in time. It might seem very contradictory that the universe can be of a finite age without a beginning, but we can transform the beginning away. I'll show you how it works. But this is all explained in this book, regarded as one of the greatest public contributions of Stephen, A Brief History of Time, record-breaking bestseller, but perhaps the least understood of all books sold on the bookshelves. So Stephen introduced, together with Jim Hoddle, the notion of superspace. And I just want to unpack that for you. So what you really do is you take the union of all curved three-dimensional spaces. So you take each space, which is consisting of a three-dimensional, say, sphere, and you put them all together. And I'll give you an example of this. and you start to be able to transform time away so that the universe has a beginning and is of a finite age, but time is unmasked. Now, the easiest way of trying to unpack this for you is to show you the eruption of a volcano called Popocatépetl in Mexico, where I've also been invited research astronomer. And you can see the volcano here, and you can see clouds of volcanic ash, and this is a time sequence. Now, what Stephen Hawking argues is that these time frames exist, and you can put them in any different order. So let's do that. You can take these snapshots in this world of superspace containing files of every single possibility. You can scramble them. So these snapshots exist for all time, right? But if you order them, then we can say, we can start delineating the passage of time. But in the world of superspace, there's no time. Those snapshots exist forever. So when I got my first Pfizer jab, after being greatly encouraged to do so by Barry Shee, that was a certain snapshot in time. And we can take my passage to where I got the jab and after the jab. These are snapshots in superspace, and they exist for all time. And sequentially, we can group them together and form what we call a time sequence. So by doing this, we can start unmasking time. So the eruption in superspace is not bounded in time. In other words, the volcano has a finite age without a beginning bounded in time in this very curious world of superspace. Let me give you another example to help you. Here's a very famous painting by Van Gogh. It, of course, Van Gogh painted it, but it's timeless. I mean, when is it? Is it depicting the Milky Way tonight? Is it depicting the Milky Way 10,000 years ago or 10,000 years into the future? Oh, no. It has a finite age, June 1889. Van Gogh painted the Starry Night, but it's not bounded in time. It could depict the starry skies then or now. So this is, again, something of a finite age, but without a specific beginning in time. It's sort of got that timeless characteristic to it. Now, the way I tackled it is very different to the way Stephen Hawking tackled this. I argued that I could understand the secret of what time is by traveling to tribes, which you might call primitive. They weren't primitive at all, but the point is they don't carry watches or did not carry watches. So come with me, and we're going to fly to Papua New Guinea, the land of the former cannibals. And I landed in Port Moresby, and then I started going up to Madang and so forth. And I was determined to understand the mindset of a very different kind of person. Just imagine this. These are locals, Papua New Guineans, and they're not wearing watches. Yet they're very aware of time, but not time as we Westerners understand it. This is the point. But they're very aware of something. But it's not the time as delineated on a watch. So how do the Papua New Guineans understand what we Westerners call time? And here you can see me standing about year 2002, somewhere around there, in the Goroka Highlands of Papua New Guinea, but no watch. See? The locals not wearing a watch. And so I was determined to probe these timeless moments in Papua New Guinea in the Goroka Highlands. And I tried to picture this. Imagine your home tonight being at the top of a tree house, which you can see here in a beautiful photograph by the legendary photographer Lint, J.W. Lint. And what is time for those three folk at the top of the treehouse? It's very interesting. When is Thursday in a treehouse? Ever thought of that? When is lunchtime in a treehouse? And then the penny dropped. And then the penny dropped is that the Papua New Guineans live in a timeless present. The only moment that matters is now. And there's actually a very interesting biblical connotation to all of this. Let me just show you this quickly. Is that the word I am. When God appeared to Moses, he said, I am. So God does not exist in time. God exists in a timeless present, just like the Papua New Guineans understand this. The only moment that mattered to the local Papua New Guineans was I am. What is happening now? They weren't concerned about the future or the past. When is Monday or Thursday? They didn't know about these westernized concepts, but they were always incredibly aware of just one moment, and that's the timeless present, I am. And the penny dropped here because I then realized this is what Stephen Hawking has been trying to say in his book, A Brief History of Time, is that you have superspace consisting of all these snapshots of the timeless present. And wearing my Jewish hat for a moment, I thought of the tension between time and eternity. You know, we bound to live in time, to think in time. But I looked at this young lady in prayer wearing her watch. And though I've never had the opportunity yet to visit Israel, I just think that there's an incredible tension here between time, the young soldier wearing her watch, and eternity, captured in our land, in our country, the country of Israel. And these timeless moments, as I've studied them, occur in different contexts. On the right, a fisherman's village at Olga Hill in Israel. Left, a fisherman. What is time to a fisherman? What is time? It only consists of the timeless present. And if you understand that without understanding any of the math of superspace, you've understood the crux of what Stephen's been trying to say, but I unpacked it in a very different way by visiting Papua New Guinea. To wrap this up, being with the late Stephen was an incredible experience. I spent time with him. He unpacked time in the world of superspace, and I unpacked time in the world of Papua New Guineans. And I wanted to know what keeps Stephen Hawking up at night. What questions, what three questions are uppermost in his mind? And he gave us these three questions. The year was 2008. Stephen asked three questions. Why are we here? Where did we come from? And where are we going? He asked us to a packed house in Muizenberg in 2008. And I thought about that. And to me, it's the ever timeless present, the I am, which gives the touch to the paintbrush, the eternal paintbrush, which strives to seek out the tension between living in domains of time as comprehended by our neurophysiological processes and eternity. And on that moment, and on that note, I hand back to Howard.
David, thank you. That was absolutely fascinating, and we've been flooded with questions. And if you don't mind, we're going to try to pose as many of those to you as possible. And let's start with the night sky, because I think our fascination, those of us who love the game reserve and go off to Kruger and we sit back and we lie back at night and we stare at that night sky. But where can we see it today in South Africa? Tell us about, does the observatory in Cape Town and the observatory in Johannesburg still exist? Can we go to Sutherland to see the night sky? How do we actually access telescopes ourselves?
Right. Now, unfortunately, all the ones you really mention in Cape Town and so forth, there is just far too much light pollution. There are, I understand, visits to Sutherland, but I don't think, I'm told that you can't actually stand next to one of these large telescopes and actually observe the night skies. They are busy. There are astronomers working and using these large telescopes. So the way to answer the question is what I did. My father bought me a little telescope. They're magical telescopes. One can buy little telescopes, you know, a Celestron telescope or a Meade, M-E-A-D-E. And these telescopes, Howard, have got go-to facilities. What that means is, if you want to observe Saturn, and if Saturn's visible, you just press, you've got a little pad, and you just, a pad, and you just press, go to Saturn. And the telescope goes zzz, and it starts finding Saturn. Or go to Mars, or go to Omega Centauri. And so, to my mind, if you don't want to invest in a telescope, the best method is to find someone who has a small telescope and to go out, for example, locally to the Magaliesberg, near Hartbeespoort Dam, somewhere where there's minimum pollution of the night skies. That to me is the ultimate. Very few people ever have access to, say, going to Mauna Kea. And even if you go, as you did, they might allow you up for one moment of one night. The astronomers are too busy. You know, it's like a medical specialist working in a theater. They are so focused on the patient. We haven't got time to show people the night skies when we are busy with these instruments. And so my answer is, what I did as a teenager when I was about 15, 16, 17, is my father bought me a telescope. And I used to stand in Krugersdorp and look at Saturn. I used to look at comets. I used to look at planets. And to me, that's perhaps one of the best ways, because the Republic Observatory, they have meetings there, but it's not a place by any means to gaze up in wonder. For example, as I showed you that magnificent image of the Milky Way from Sossusvlei, or the Milky Way from Namibia, you just don't get that. The quiver trees, you just don't get that in our cities. Visits are allowed apparently in Sutherland, but you can't see what I've shown you tonight. The best option is to find someone with a small telescope, or otherwise just to buy a small telescope. They are not that expensive.
So now, David, let's almost go through different segments. And a lot of people have asked tonight about life, or the potential of intelligent life on other planets. Yeah. What's your take? Is there potentially intelligent life on other planets? And could we, if there is, discover that in our lifetime?
That's a question which has been asked for centuries already, is, does life exist on other worlds? Now, the bottom line here is that we've discovered dozens of exoplanets. These are planets orbiting other stars. We've observed them, but we've inferred the existence. So we know that there are many stars with planets around them. But to generate intelligent life is another process entirely. Nobody knows, not even Richard Dawkins, nobody knows how life starts. I've asked some of the world's greatest minds about this. Nobody can tell you what is the spark that starts the process. Nobody knows how life starts. So because we don't know how life starts, we can't infer that the universe, as big as it is necessarily teeming with ETs. That would be false. You know, when I grew up, I looked at the planet Mars, and we believed that, you know, Mars, well, Lovell and others believed that Mars might be inhabited by an advanced race of Martians. And that, of course, was totally disproved. So, yes, we found that the universe contains myriads of planets around stars, but we don't know how life actually kickstarts. I like to take a rather biblical perspective, which is so that God creates, much like in Genesis, God creates. God gives the spark. That's how I like to think of it. And
so, yes, Professor, if I can interject there, when we look at these planets, some of them are in what's referred to as the Goldilocks zone.
Right.
Not too hot, not too cold,
Absolutely.
not too far. Not
Absolutely.
so those are the most likely ones, should there be life.
No, I mean, that's right. But you see, the point is this. Mars, many regarded, was in the Goldilocks zone, just a comfy spot. But when we landed on Mars, we found nothing, right? There's no Martians there. So we have to be very careful. When we infer that the conditions are right in the Goldilocks zones, you cannot jump to the conclusion that there's another Howard out there. That's a totally, totally different question whatsoever. And any astronomer who says there is intelligent life out there is someone who would not be warmly accepted by my colleagues, because we simply don't have the answer. I like to think that there might be intelligent life out there, but because I understand so little, because my colleagues, including biologists, understand so little of the intricate processes of the origins of life, we need to be very cautious. We often say the universe is so large that it must be teeming with life, but that's also fallacious. My students are often given a little exercise. I've asked them, Howard, how large must the universe be to contain just Howard? And the answer is, the universe, just to contain a person like Howard or Donnie, must be around 14 billion years in extent, just to contain you. So we simply do not know.
So now the next part of science, or the big challenge of science, is to unify the theories between what we know about the massive and the tiny.
Right.
What we know about the huge galaxies and quantum mechanics on a very small scale.
Right.
Explain to us in 1 minute, if you can, what is string theory?
So the quantum mechanical side of things is extremely important, because general relativity only holds on large scales. And so you have to go down to really macroscopic scales, and that's where the world of, Pam Dirac and others kick in. And so essentially, they're flow lines of energy, if you like to think, called little strings. And it's a way of trying to understand how the early Big Bang actually develops, how it unfolds as a function of time. And it's been theorized that you've got these little flow lines, as it were, of energy, strings. And as you saw, our universe consists of the cosmic web. And you've got myriads of these filamentary structures. So if you transport that back to the earliest of times, you can imagine like a tiny little ball of strings. All of these would give rise to galaxies and stars and planets later on. Again, string theory is extremely interesting to discuss from a mathematical point of view, but whether strings actually exist in nature, we don't know. It's simply a very elegant mathematical tool to try and understand the evolution of the Big Bang at very early times.
So, Dave, understanding what we do now, we developed something called the Large Hadron Collider.
Yes.
And we went in search of the God particle, the Higgs boson particle.
Right.
What did we learn when we discovered that it actually existed?
That's extremely interesting. I mean, the whole idea of the God particle is just absolutely fascinating. And to my mind, it's actually challenging our minds. Does it confirm our current understanding of physics, or does it not? And my take on all of this, the discovery of the God particle and so on, is that we still are at a 4% level of understanding of what's really out there. The whole arena of dark energy and dark matter remains to be explored. And so while the God particle was a very exciting epoch, to study the constituent components of atoms, and it sort of helped unify our understanding of the early Big Bang. So that's what it did. It helped unify our understanding of the early Big Bang. We've still got such a very, very long way to go.
So let's talk about time travel. Einstein was the one who explained to us that time gets warped by gravity. Mm-hmm. This idea that we've all grown up on, that we can travel backwards or forwards in time potentially, is that I understand a theoretical concept, or
Right.
is it a practical concept? How does time travel work?
Yeah, now, in other words, suppose you have a pair of twins, and one twin stays on Earth, and then you jettison the other twin into an imaginary spacecraft, and you jettison your twin to close to the velocity of light. Then time starts dilating as the inverse square root of 1 minus v over c all squared. And what happens then is that the watches tick slower and slower. The twin's watch, the twin is traveling very fast. His watch or her watch starts ticking slower and slower compared to the other twin's watch on Earth. And so the twin who comes back will be younger than the twin who remained on Earth. That's one example of time dilation. Time is not a standardized concept. This is what Einstein was great at, is that time itself moves, it flows, but a second for Dave Block is not necessarily a second if you're in a spacecraft traveling at high speeds. And that's an example of, let me also explain this to you, how it is that whenever we look at the universe, we're looking back in time. We're traveling back in time. When I look at our sun, I travel back with my eyes 8 minutes in time. When I look at the Milky Way galaxy, I travel back in time. When I look at Proxima Centauri, I travel 4 light years, 4 years back in time. When I look at the Virgo cluster of galaxies, I travel, 20 megaparsecs, that's 3.26, that's 60 million light years, 60 million years back in time. So I'm always in this time machine. I'm always looking back in time. And what Einstein showed is that time dilates the faster you travel. And so time is relative. That's the key. And that's why we call it the general theory of relativity, or the special theory in Minkowski space-time of relativity. It's not a standardized 1 second concept. That's really the whole key to all of this time travel.
And the faster you travel, the slower time becomes.
Exactly. Time dilates. In other words, 1 second to someone traveling at, say, half the speed of light is a lot longer than you would experience 1 second on your watch. And that's why when the twin brother or sister comes back, he or she is much younger. It all fits into what Einstein showed us, is that nothing's standardized. In Newton's mind, everything was standard. F equals ma, or F equals ddt of mv, the first derivative with respect to time of momentum. That's standard, ddt. It's a standard unit of time. Einstein completely detonated that idea.
So now your cousin Barry has asked 2 questions that he wants you to explain.
Yes.
One is gravitational waves.
Yes.
And the second is, what is this concept of the multiverse?
All right, so let me start with the second one. Is Stephen Hawking was able to show that we live in a very, very finely tuned universe, very finely tuned. But, and here I'll tell you something which you might not have known, Stephen, when he discovered that we live in a very finely tuned universe, decided he wanted to expunge God from the equation. That's true. He says so in his book, What Place Then for a Creator? He actually ends his book with that. So he aims to expunge God. Now, the way that astronomers have tried to address the existence of our very finely tuned universe is by means of the multiverse. So imagine our universe being a bubble. I would argue that it's the only bubble. Very finely tuned. Our universe is designed. I'm completely committed to that understanding of the cosmos. But Stephen agreed that it's incredibly finely tuned, this bubble. So the way Stephen tried to answer the question was as follows. He said, well, look, if it's very carefully designed, there must be a designer. So how do we expunge God from the equation? Well, we imagine other bubbles the existence of other universes floating in my screen, other bubbles, and we just one bubble, one universe amongst myriads of other universes, and that's the multiverse. But here's the rub. I believe that the multiverse belongs to the domain of science fiction, because when I grew up as a student of applied maths and astronomy, we used the Baconian method, which means everything we do is subject to the Baconian criteria of testability and observability. If I say, for example, if I take this and I say, here is my hard drive, my Lassie hard drive, you have every right to say, David, this doesn't exist. But then I can bring this to you, or we can sit in the same room and you can say, all right, let's feel it, let's check its dimensions and so forth and so forth. And we can prove with one another, we can observe, we can test, we can prove that the Lassie drive actually exists. The multiverses are all imaginary, can't test them, it's untestable. And so together with Professor George Ellis in Cape Town, I believe that the multiverse belongs to the realm of science fiction. I don't take it seriously at all. It's a mathematical construct. You can get incredibly interesting little bubbles, but I look at the philosophy behind the multiverse. And I can honestly say, having studied this very carefully, is that the multiverse was really developed. It's very interesting. Stephen was committed to expunging any notion of the creator from the story. And he did so brilliantly in his own mind, using the world of quantum mechanics, giving rise to the multiverse. But if I said to you, this room is, there are fairies all over the room, you'd say, but David, I can't see the fairies. Where are the fairies? Of course, they wouldn't be here because you can't, they may be here, they may not be here because you can't see them, we can't test them. And that's exactly the same with the multiverse. So I believe that if we start studying the multiverse seriously, I like to look at the world of science versus scientism. Science is the discipline I grew up in. Scientism is injecting atheistic philosophy into science. That's very different. There's a very big difference between science I grew up in and with, and scientism, which tries to inject personal philosophies of atheism into the agenda. And I believe that's where the multi-universe fits. Now, with regard to Barry's other question of gravitational waves, this is very interesting.
And he wants to know how do we measure them? That's part of his question.
Okay, so the idea is that, for many years, we know that gravity, we of course know from Newton's days and so on, gravity propagates through space. And we understand the mathematical formulation of gravity. But again, just like with dark energy, what is dark energy? And again, the question arises, what is gravity? And it has been posited that gravity propagates spatially in a wave-like structure. And again, we have got detectors on Earth which can detect gravitational waves. We can fill containers with large amounts of certain liquids, and we need to have them. I mean, I remember, for example, one of my mentors early on in Wits was Professor Friedel Selshop, and he used to go down deep into mines, and he would actually be able to try and detect neutrons deep under the mines. And so we have these gravitational wave experimental detectors. They're there. It's the way in which gravity actually propagates through space-time, but there's still such an incredibly long way to go to actually understand. We have the mathematics, but the physics is not there yet. How does gravity actually propagate in these waves in space-time? As I say, the experiments such as LIGA and so forth, which have detected these gravitational waves, but we're still a long way from definitively detecting them. We detected them, but we're still a long way of understanding of the actual physical constituents of the propagation of these waves.
So, Dave, we've had 3 questions relating to sunspots.
Yes.
The one question that come up is it possible that climate change may be the result of sunspots? That's one question.
Okay.
Before you answer that, The second question is from a radio astronomer, or and he says that in fact we should at the moment see much more activity on the sun, because the sun goes, if I remember correctly, in 7-year cycles of 11.1 year cycles of high intensity going down, and we should see much more activity on the sun at the moment, but we're not. Why is that happening?
Well, first of all, sunspots would be totally unrelated to climate change, because the sun has got, the sun goes through, let me explain. The sun goes through a cycle, an 11.1 year cycle. There's maximum sunspot activity, and then it decreases minimum. And sunspots are just magnetic storms on the sun. They're cooler than the surface of the sun. The surface of the sun is around 6,000 degrees centigrade. The temperature in a sunspot is around 4,500 degrees centigrade. It's cooler, and therefore it's darker. And the sun goes through these 11.1 year cycles. But, and here's the rub, climate change would be induced by, for example, holes in the ozone layer and so forth, carbon emission and so forth. So climate change is induced by us depositing lots of junk into the atmosphere. It's got nothing to do with the sun. What the sun does do, and what the sunspots also contribute to, is the aurora borealis. Now, I take groups every year to see the aurora. I've taken groups of radiologists. I took about 2 years ago a group of 30 gynecologists. We flew up to the Arctic. We were 20 degrees from the North Pole. So sunspots, when you've got maximum sunspot activity, you have incredible amounts of aurora, but it doesn't affect climate change. Climate change is a result of, as I say, us depositing large amounts of junk into our atmosphere. If we weren't, there wouldn't be all these catastrophic changes in climate. The sun is pretty stable, even though it goes through the cycle. The solar wind is pretty stable as a function of time. So it would be wrong to infer that climate change is induced by any changes in the sun. When the sun does have a massive sunspot activity, it does affect radio reception on Earth, but definitely not temperature changes. The sun there is pretty stable. The sun's activity is variable, and it goes through a Maunder cycle of MAUNDER of 11.1 years, but you can't predict it. I've been in the Arctic when the sun is almost free of sunspots, and we have incredible auroral activity. And I've been there where you have a lot of sunspot activity, and there's not many aurorae. So it's a very variable phenomenon, sunspots. And so you can't just use predictions to say, all right, the sun should be covered with sunspots. Now, it's variable, and that's what's so exciting. You must understand, as I've explained earlier, that the sun is this seething, writhing sphere of hydrogen gas, and helium's been fused into it at the center of, at its center. And there are model predictions. In other words, one can say, all right, according to statistics, there should be so many sunspots on the sun. But if there isn't, it doesn't matter, because it's a dynamically open system, if you like. There are so many variables.
I must say, going to see the aurora is probably one of the greatest experiences of my life. Minus 40 degrees in Tromsø in Norway, and but when the sky explodes in dancing green light, there is nothing in the world that ever compares to that.
I agree with you, Howard. Did you see other colors as well?
No, I never saw the purples and the reds. Only saw the green, but it was still
it's interesting that
magnificent.
You mentioned Tromsø. I am taking a group in February, I think February or March next year, if COVID permits, to Finland. And we're going also right up north. And there is nothing to describe this absolute bursting of color. You just look up, and then here's an aurora, and then there's an aurora, and here's an aurora, and there. And it's just, now what's happening there is that high energy particles from the sun, such as xenon and such as krypton, are hitting our Earth's traveling along the magnetic field lines of our Earth and hitting our atmosphere and ionizing oxygen and so forth, and giving rise to the greens. And you can see yellows, and you can sometimes see reds and so forth. But to me, that's a wow experience, which everyone hearing me should actually go and see. I love taking my groups up north.
It was a birthday gift to myself, and the greatest gift I think I've ever given myself. So here's an interesting question. Let me find it, and it's about if there were a huge mirror. This is from Hugo. If there were a huge mirror on a distant galaxy reflecting back to Earth, could we see our past?
Only insofar as we are always looking up and looking back in time. So in other words, if I look at the sun, I'm looking back 8 minutes in time. So you don't even need a mirror. When you're looking at the sun, if, for example, a solar prominence leaves the surface of the sun at noon, it didn't actually leave it at noon. It left it at 11:52, but it takes 8 minutes. So you're always looking back in the past. And that's the wonder of astronomy, Howard, is that whenever I look at, for example, the Andromeda Spiral Galaxy, I showed you, I studied that, and the results were published in Nature. The Andromeda Spiral Galaxy, we're looking back 2.2 million light years, 2.2 million years in time. So if you were to able to say, look back 65 million years in time, and you could, then, for example, you'd see the dinosaurs on Earth, right? At the Cretaceous tertiary boundary, you'd actually see the dinosaurs. So the answer is absolutely yes. We never in astronomy look forward in the sense of looking into time. We're always looking back into the past. And that's the amazing thing. When I'm looking at the moon, I'm looking back in time, but just a fraction of a second. But when I'm looking at the sun, 8 minutes in time. When I'm looking at the Andromeda Galaxy, 2 million years in time. So if I take a galaxy, which is, say, 65 million light years away, and if there were dinosaurs on it, I'd be able to observe the dinosaurs theoretically if I had a telescope of good enough resolution, which we don't have. It's always looking back in time.
So an anonymous person has asked this question. You said the universe is ever expanding and accelerating.
Yes.
What are we expanding and accelerating into?
All right. Now that's a very, very brilliant question. Now let me just explain it as follows. Our three-dimensional minds think of embedding. Let me explain that. If I say to you, Howard, think of a chair, you think of a chair and then the space around the chair. Now, let me posit this as an analogy. Take the universe and think of it as a balloon which is ever expanding. And you paint the balloon with little dots. And each little black dot is a galaxy. Then as you blow the balloon up, one black dot recedes from another black dot, right? You blow your balloon up. Now you ask me, Dave, what's outside of the balloon? Well, let's ask an ant on the surface of the balloon this question. If there's an ant on the surface of the balloon, the ant, if you say what's outside, the ant says, well, I have to explore. And so the ant moves on the surface of the balloon, goes round and round and round and round and round. And you discover that you're living in a universe which is finite and unbounded, but there's no outside in this direction. You're constrained to live on the surface of the balloon. Another example is this. If you, for example, take a wedding ring, you can see it there maybe, and you put an ant on it, you put a little ant on the ring, you say, what's outside the ring? There's no outside to the ring, to the ant. See, we think of the ring embedded in space and time. But if you put an ant on the ring, the ant goes round and round and round and round. And the ant comes to the conclusion that he's living on an infinite universe, in an infinite universe. Where our minds play tricks on us is that we keep on thinking of the universe as being embedded in space. That contradicts the definition of universe. Universe means the sum total of all space and of all time. of all space and all time. And so the best analogy I always give my students of when they ask me this question, Prof, what's outside, is explore. And if you're an ant on the balloon, an inhabitant on this expanding, accelerating universe, you say, what's outside? Well, you start walking, but you can't leave the universe. Do you get the idea, Howard? You can't leave the surface of the balloon. You're constrained. You're constrained to move on and in the surface of the moon. We three-dimensional creatures can't leave the universe. We can't transcend. We can travel within the universe. We might be able to travel in due course hundreds of, millions of kilometers. We don't know yet. But the key point is there's no embedding of a universe in pre-existing spatial frameworks which are larger than the balloon. That's where our mind plays terrible tricks with us. You must understand this, that Einstein's great breakthroughs, of course, were multitudes, but the whole idea of space-time and the curvature of space, that's goes against intuition, doesn't it? We tend to think of, how can space not just be flat, or space, how can it be curved? Again, our finite three-dimensional minds do not readily understand these concepts. But the best analogy I can give you, which I give my students, is that of the expanding balloon. Put an ant on the balloon, there's no outside. Just like there's no outside, the question of what was God doing before he made the universe also doesn't make sense, as I've explained earlier.
So one of the things you referred to earlier is the star Betelgeuse, not too far away from us. And Betelgeuse is likely to become a supernova.
Well, the point is, Betelgeuse is very massive. Its radius is probably around nearly 1,000 times the radius of the sun. And so any star whose mass is larger than the Oppenheimer-Volkoff limit of 2 solar masses, that will then become a black hole. But if it sheds a lot of its mass, like in the Helix Nebula, it can collapse to form a white dwarf. It largely depends on the mass, the spatial structure of the mass inside Betelgeuse and its actual mass. But if you've got a massive star like Betelgeuse, the probabilities are so high that it just collapses inward and inward and inwards to form your black hole. If you have, for example, a star whose mass is, say, twice the mass of the sun, of course, Betelgeuse is much more, then it can readily explode and form a neutron star, as happened in the Crab Nebula in Taurus. Yeah, so you've got the 3 possibilities: the white dwarf, the supernova, the neutron star, and then the black hole, all dependent on, is it less than 1.4 times the mass of the sun? Is it less than twice the mass of the sun? Or is the parent star greater than twice the mass of the sun, which is the Tolman-Oppenheimer-Volkoff limit?
So there's a question that Paul has just messaged me, and he says, does matter become energy at the speed of light? But isn't matter all of energy in essence?
Yeah, so what we speak of in general relativity is mass energy. In other words, Einstein was able to show, this is the whole thing, Bayer equals mc squared, and I know you've got a book, a top favorite, which has that in its title, equals mc squared, is that they're interchangeable. It's got nothing really to do with the speed of light. It's just that, if the temperatures, densities, and pressures are right, like they are in the center of the sun, you can create energy from matter, right? Hydrogen fuses into helium. It doesn't have to do anything with the speed of light. It fuses because the temperatures are so high and the densities are so high at the center of our sun that you've got thermonuclear fusion. Therefore, in classical mechanics, we speak of a mass of little m, and then you use Newton's first law or Newton's second law or Kepler's laws and so on and so on. But when it comes to, for example, relativistic astrophysics, we speak of a mass energy. In other words, we can speak of a particle with a certain mass, but you could also think of it in terms of what energy would it give if it was fused or transmuted into energy. And that's why you've got the equivalence, right, between mass and energy. And that's really the heart of understanding equals mc squared. But you really need the correct astrophysical conditions for that to happen, which are often, for example, in stars, cause of high temperatures and high densities, and that ignites the thermonuclear fusion.
So, Dave, if we can go back to almost the first topic that you started with, black holes. We now know more and more, and we have images. The first image of a black hole now, and at the event horizon, let us say I was sucked in. What happens? I presumably get crushed, but black holes, do I not get crushed? And black holes also exit energy.
Okay,
explain that process to us.
All right. Now let's avoid a little bit of Taurus here and get this straight. Is that when a black hole forms and it's rotating, we call them Kerr-Newman black holes, there's this event horizon. And in the Schwarzschild case too, there's this event horizon. Now, what this means is as follows. Let's take an astronaut. When an astronaut crosses the event horizon, he or she may not know that they've crossed the event horizon. They may not know. Remember, the density of matter at the event horizon scales as 1 over the square of the mass. So if you've got a supermassive black hole of billions of solar masses and you square it and you take its reciprocal, the density might be less than that of air. It's true. So imagine you're traveling just like this, and you just calmly travel in, past the event horizon. No alarm bells would ring, except if you try and ignite your engines to get back, you'll find you can't. So you'll never experience in your spacecraft any alarm bells ringing as you cross the event horizon. But the event horizon is the trapped surface. You can't escape once you've crossed the event horizon. So once an astronaut crosses the event horizon, he or she is propelled inward and inward and inward. And we can actually prove that R dot, which is the RDT, which is the rate of change of radial motion with respect to time, is ever inward. And you get crushed at the singularity, which is really at the heart of the black hole. It's a point-like structure in a non-rotating black hole. It's a ring-like structure in a Kerr-Newman black hole, and so forth. But the idea is, Roger Penrose, of course, is the greatest mind on singularities, is you get crushed as you approach your singularity at the center. But at the event horizon, no. Very interesting. You can actually go in a spacecraft, talk like we are talking now. You wouldn't know anything. You'd be totally untoward of anything happening, except that you can't get back out. Gravity wins. That's what happens at the event horizon.
But we have seen evidence of gas and energy being shot out of black holes, have we not?
Well, you must understand what's happening there is that you've got these accretion disks. So you, for example, have a massive star and the black hole sucks in matter from the star. It flows through what we call the Roche limit, the Roche lobe. It flows through and it starts circling the black hole. And then you get that glowing accretion disk, which you saw. You saw that in the first picture of a black hole in Messier 87. You saw that bright orange ring, right? And then you
and brighter at the bottom.
That's right. And so what's happening there is that matter is spiraling in around the black hole, emitting vast amounts of photons. And so it appears bright to us. We can see it. We can't actually see the black hole itself. That's dark. And you can see that in the actual image. Yes, if black holes are rotating very fast and so forth, they can start spewing out, you get this with neutron stars, spewing out certain jet streams of gas, say in this direction and then in that direction. But the key point here, Howard, is that you'd never observe the actual constituents of matter as they cross the event horizon. You're always observing what's happening outside of the black hole, as in the famous April 2019 image.
So Prof, a lot of questions have come in as well about going to Mars.
Yes.
Why are we going to Mars? What will we learn there? And is it a good use of our resources?
Well, You know, I've never quite understood this one-way ticket to Mars. I've met people who want to go on this one-way ticket to Mars, but it's mishugas to me. And I'll tell you why it's mishugas. I mean, I can't think of anything worse than a slow suicidal death. And I know I might be sounding very controversial here, but I really understand the physics and the maths, is that when you land on Mars, you can't take out your spacesuit, off your spacesuit, because the atmosphere is just totally different to the atmosphere on Earth. You'd die within a microsecond. And so you'd have to construct buildings. There's no hotels to go and relax in and so forth. So mankind is an explorer, right, Howard? We always explore. We want to know what exists on other planets. Was there water? Was there once running water on Mars? Because if there was once running water, people often try and infer that there was life once on the planet Mars. So I'm much in favor of a two-way ticket to Mars, in the sense that you can go, you can explore, you can take spectrophotometric samples of certain rocks on Mars and so forth, but samples, and study them from a spectrophotometric point of view in labs and so on. But to actually go with a one-way ticket, and you've got to construct everything you're going to live in. You have to construct your buildings, you have to generate your own artificial Earth-like atmosphere and so on, is to me a slow suicidal mission. Others disagree. I mean, I've met people who want to do this. Also, think of sending a WhatsApp. You send your WhatsApp and then you wait a long time, many minutes before you even start getting responses back. It's just, to me as an astronomer, the way I tackle this is I use my telescopes. And so I can sit in the comfort of my home and explore. These people actually want to go to Mars, for example, and explore. And I've got nothing against that. But when it's a one-way ticket and you can never come back, I can't understand the logic behind it. But again, there are people who want to do that.
So let's talk about the billionaire space race at the moment.
Yes.
Is there any point to this, or is it all about ego? I mean, you see people like Richard Branson going up, and he's not even in real space. I mean, he's towards the outer edge of it's not really technically space he's going to.
Correct.
Is there any point in spending billions and billions of rands to send these billionaires and a few other billionaires into the atmosphere so they can float around for a few minutes and then come home?
You know, we live in such a paradoxical world. You know, when I traveled to China to lecture at the Tsinghua University, I really had to beg and find sponsors to pay for premier economy class. They could never afford to send me business class, never. I don't think I've ever traveled business class in my life, maybe once. You never find the money for it. And here, you're spending 220 million rand, 400 million rand, and so on. At the moment, Howard, I don't see any scientific or any science coming from these missions. It's really billionaires who are having fun, right, in space. But wearing my hat, and I'm doing this seriously as an astronomer and astrophysicist, I don't really see any benefit to us understanding the large-scale structure of the universe, or understanding the motion of stars or galaxies or planets or anything. I'm all in favor of the International Space Station, because there we can at least conduct experiments. And I think what Mark Shuttleworth did was admirable, in the sense that he spent time on board the International Space Station. But I don't think it's the best use of money. I mean, when you're looking at that sort of money for 10 minutes, if I was given that money and I channeled it, for example, into specialized telescopes and trying unlocking the magic of dark energy and dark matter and so on, I think that leads to a sense of opening the shrouds of the night in terms of a scientific perspective. But you must, I mean, you've put it so beautifully. You go up for 10 minutes. you reach the outer sort of layers of our upper atmosphere, and you come down again. And I mean, I watched this very closely with Jeff Bezos when he came down, as he touched down, and he said, that was great. Well, I mean, it was great, and he's got the money, so let him use it as he sees fit. But I just, you know, I look up at the universe and I do understand so much of what is going on, and I can see such better ways of using money, not only to improve our understanding of the universe, but to avoid, for example, to try and stop climate change. I mean, just think of these incredible forest fires, veld fires, if you like, in California, and then the raging smoke in Athens. There's so many drastic things we need to spend money on, including Barry's field of vaccinating. I mean, you know, here we're sitting with a joyride, and nearly all of Africa is largely unvaccinated. So where's the balance? And that's what I'll try and present to you, my listeners, this evening, is where's the balance in all of this? Where's the science in all of this?
So, Dave, we've got about 8 minutes before we have to send you on your way back home, and hopefully Eskom hasn't turned off the lights on the journey. Yes. But if we can try and get through a few questions, I first want to start with the SKA, because it's a South African project. It's one of the greatest investments in science in South Africa. So tell us a little about the SKA. And after that, there have been so many questions about people who want to go on one of your trips to see the Aurora Borealis. We want to discuss that as well. And then there are a few little questions I'm going to fire at you, hopefully to get 10-second answers on.
All right. So maybe you could put this up on your webpage. I have a webpage, www.davidblock, David, and then it's B-L-O-C-K, not Bloch, but Block, www.davidblock.co.za. Maybe you could put that up. Now, anyone listening to me from around the world can reach me. And all they need to say is, hi, Dave, I'd love to come with you on your next Aurora trip, or your Aurora trip in 2022 or 2023 and so on. And I'll immediately respond, and you know, 12 months elapse, and then you come with me to experience the magic of the Northern Lights. There isn't anything like it. So the way to book for those is to send simply an email to, if you go to my website, there's a way of contacting me by means of email, sending me a little message. There's a contact button. Just contact me on www.davidblock.co.za. And yes, I mean, it's the greatest privilege I've ever had, is to show radiologists and gynecologists and members of the public the magic of the Aurora. Your first question, how it was
the SKA. It's a South African project. Yes. It's expanding our knowledge and our investment in science in this country.
Absolutely. Now, there is very good use of money, and it's literally an array of telescopes. You've got a square kilometer array of radio telescopes. They're not optical, they're radio. And so they're going to give us they're going to unlock unique secrets of the evolution of our early universe billions of years ago. And I have the greatest of respect for our SKA leaders. I think I remember the miracle of hearing the news that South Africa would be hosting most of the SKA. There's some dishes, for example, in Australia, but they'd be hosting most of the instruments here in the Northern Cape and so forth. And yes, I think being radio telescopes, for example, that picture I showed you of Messier 87 uses those radio dishes, right? Those antennae. And just look at the magic we were able to unfold. The first picture of a black hole, but that's using radio, very long baseline interferometry.
And because you take an atomic clock and you synchronize all your radio telescopes around the world onto the same atomic clock.
Exactly. And that's what you have to do with the SKA as well, is that's brilliantly put. You've got to synchronize every single package of data, because you have to, if you're seeing, for example, in Messier 87, a certain area of your accretion disk, you have to put together all the snapshots taken at that specific same moment. But some are coming from Spain, some are coming from Hawaii, some are coming from the South Pole. So you've got to simulate. So the computational techniques behind instruments like the SKA are absolutely first-rate and absolutely world-class, because you've got to synchronize everything. They act as one giant antenna in the end. You've got to synchronize. And I have the greatest of hopes that the SKA is going to give us a very important new window into matters of how did galaxies form? When did the first stars start to shine? We're not exactly sure of the answer to that question. When did the first stars start to shine? Also questions of the large-scale structure of space-time, the filaments, the webs-like structure I showed you. It's going to unlock myriads of those secrets. And I've been very privileged. You know, I've served as, well, I don't know if I should say this, but I've served behind the scenes in reviewing certain scientific proposals and so on. And I'm deeply encouraged by what is happening at the SK. I think it's South African, that's the key.
So Dave, if I can fire one or two short questions for very short answers, some of them, to be quite honest, I don't understand, but I'm going to end with a question after that maybe you want to contemplate. Within our lifetime, what do we hope to solve? That's where I'm going to end. But before we do that, Shimron is asking a question about Stephen Hawking's breakthrough starshot initiative. I don't know anything about that. Do you have an opinion about that at all?
I didn't know anything about that either. His starshot initiative, I've not heard of that from the mouth of Stephen Hawking. And I'm in the dark, as much in the dark as you are there, Howard. I would be totally ignorant to make any comments. I've never heard of that. Of course, I've heard much of Stephen Hawking's breakthroughs in terms of superspace and space-time and primordial black holes and singularities and so on. But I haven't heard of a starshot, so I'm not sure that's really to be attributed to Stephen Hawking.
Rael Weinberg, who's watching us from Canada, asks, what about a Jupiter opposition event tonight at 8 p.m. in Canada Eastern Time? I don't know if you know anything.
Yeah, so it's a unique opportunity. Jupiter's going to be exceedingly, well, not exceedingly, but it'll be nice, very bright, and relatively nearby. And so astronomers refer to this as being in opposition. It's relatively bright, it's nearby. And so it's the best opportunity, in quotes, to capture Jupiter and its moons, because it's nice and close and it's nice and bright. The planets follow elliptical orbits, and A cubed goes over T squared, where A is the semi-major axis and T is the period. And so in opposition, you've got a nice bright object relatively close. Take a 600 or an 800 millimeter lens. You can start resolving Jupiter's moons, nicely so in opposition, such as Ganymede, Io, Callisto, and Europa. Europa covered in water ice, Io fiery red in color. So that's what Rael and others will be able to photograph tonight, hoping for clear skies in Canada. Oppositions are great moments. The objects are bright, they're close, ideal photographic opportunities.
So Dave, before we answer the very last question, a few people have posted about amazing astronomical experiences that they've had in South Africa. So Guillermo tells us that from Cape Town, he runs astronomical tours, or astronomy tours. So that seems like an amazing thing to try. Also in Prince Albert, there's astro tours, and a few people have told us they've gone with Hans Santilani on astro tours and had amazing experiences. And I think for people who want to follow, there's obviously yourself, and there's a lot of, you've written books and there's material. If you go onto YouTube, there's a lot of stuff. Neil deGrasse Tyson, the former.
I was just going to mention his name. I think that he is, so that's Neil and then deGrasse, D-E, and then G-R-A-S-S-E, and his surname Tyson, T-Y-S-O-N. Neil is
he was former head of the Hayden Planetarium in New York. It's now in Washington. Very accessible
very
information.
Accessible. And you know, you asked earlier, one of your listeners asked earlier about Patrick Moore's influence in my life. He played a very prominent part in the formative stages of my career. Patrick was on the BBC for 50 years, I think. The Sky at Night program ran for around 50 years. Patrick's moved on. And so in the United States, we have Neil deGrasse Tyson and
also Bill Nye. Let's not Bill Nye, the science guy, and also Brian Greene.
Absolutely. Brian Greene has written just so many books, including books on the subject you asked me about earlier, the strings and string theory. Brian Greene is an absolute master in that. So there are, I mean, for example, if I went onto Amazon tonight, there are myriads of books, apart from mine, Shrouds of the Night, but there are myriads of other books you can also order. You just, astronomy is so diverse. If you're interested in strings, you type string theory and myriads of books will come up. If you look at Neil deGrasse Tyson's webpage, myriads of topics will come up. And I'm so pleased to have devoted probably nearly my entire life to the communication of astronomy to the public. And I think the lectures you attended, Howard, you saw that we had packed auditoria of thousands of people per sitting. There's such an intense interest in science and in astronomy. And that's why even tonight is a singular honor and pleasure for me to be discussing this tonight. But there's no dearth of materials regarding astronomy. It's all out there. And the tours you mentioned, yes, there are many people there, even tours to the Cederberg. I mean, I'm aware of all these different tours. But the most magical one, and it's not just me saying this, but the most magical one is certainly, as you've said as well, the aurora. Why don't we go to the Antarctic? There's no real landmass to land on and have hotels in. But in the Arctic, we can stay in the most awesome boutique hotels, and then I take you out at night. We dress appropriately so that you don't get cold, and we look up at the aurora. So that to me is the way to move forward in astronomy. It's so accessible by means of books, by means of telescopes, even small telescopes, as I've said. And it's always that sense of looking up in awe and in wonder.
So in conclusion, Dave, within our lifestyle, within our lifetime, what is the great mystery that we hope we'll solve?
Dark matter might be solved tomorrow. I don't know. Dark energy might be solved tomorrow. I remember talking to Nobel laureate, one of the Nobel laureates who won the prize for dark energy, Brian Schmidt. He's also at the Australian National University. I've sat with him. I've sat with Kenneth Freeman, this great colleague of mine, who's one of the greatest minds in dark matter. And I don't know. I mean, that's the wonderful thing of astronomy is nobody would know that during the lifetime of Einstein, that an Einstein would emerge. You just don't know. Nobody knows when the next Newton will emerge. But one thing gives me great hope. And here's something, a nice little point to end on, is that so many Nobel laureates have been good boy chicks, boys and girls, Jewish people around the world. And it's a privilege. I always say this. It's a privilege to be a Jew and to be studying the night sky, because there's something there. There's something there that touches me, and it just ignites my spirit. And yeah, I wish I could tell you what we'd solve in the next year even. You've been to some of the great telescopes which I've used. You've been there, you've stood there. But who would have known that Watson and Crick would crack the DNA code? Who would have known that? Who would have known that Rosalind Franklin was so, I mean, this is one of the greatest senses of, I get verklempt in Yiddish, overcome with emotion, verklempt. When I think of Rosalind Franklin, she died of ovarian cancer, as I recall, and yet it was her X-ray which led to the cracking of the DNA code. And she went unrecognized at the Nobel reception, largely unrecognized. Books have been written about this. But nobody knew that there'd be this young Jewish girl, Rosalind Franklin, who was really the mastermind in her famous photograph, the fraction photograph of the DNA. So this is the wonder of being a scientist, is that you ask what's going to happen in your lifetime, I ask what will happen tomorrow. Maybe tomorrow I'll be in touch with someone from Harvard, and maybe tomorrow we will have unpacked dark energy or dark matter. That's the wonder of science. It goes on an unknown trajectory where the future is spring, but we never know when the new dawn of unlocking the next great mysteries will unfold. But to cap this and bring it to a finale, what do we know? What don't we know? I've elucidated so much of those tonight, especially dark energy and dark matter. And there's no better time to be alive. Let me say this in conclusion. There's no better time to be alive than now. The technology we have at our disposal, even though I have to beg for premier class economy tickets, even though I yet have not been to Israel, even though I travel to all parts of the world economy class, the technology is there. We've got these incredible telescopes and we've got these incredible minds. That's what I like to end off with, is we've got people with incredible amounts of DNA, of intellect, to try and unlock the mysteries of the cosmos in which you and I live, move, and have our being. We think of the great questions asked by Stephen Hawking. Why are we here? Where are we going? And where did we come from? Thank you, Howard.
David, thank you. Tonight, you not only unlocked the mysteries of the universe, but I think you unlocked many of our minds as well. And one of the things that I take away from this is the trajectory is of expansion. Time goes forward.
Right.
As do we. And we learn from those who come before us, and we go and explore, and we create within our own minds and our own understandings even greater universes. David Locke, thank you so much for joining us this evening. Thank you for being so generous with your time. It's been such a pleasure to deal with you. Thank you to our audience as well. Please, we ask those of you who've managed to stay late with us this evening, leave us a comment. We really appreciate everything you've done for us, Dave. Thank you so much, and really enormously grateful for the wisdom and the insight that you've given us.
It's been
Have a good night.
Absolute honor. Shalom. Good night.
Cheers. Good night. Night, everyone. See you later in the week at our next webinar.